far beyond our small corner of the universe, amid the boundless stretches of space, exist objects so extreme and so mind-boggling that they push the very limits of what we understand about the cosmos. Among these celestial wonders, the neutron star stands as one of the most fascinating. An object born from the catastrophic death of a massive star, yet so compact and dense that it challenges everything we thought we knew about the universe. Imagine this: a star once blazing in the night sky, its core collapsing under its own immense gravity, leaving behind a dense remnant, an ultra-compressed ball of neutrons with a mass greater than our sun, squeezed into a space only about the size of a city. A neutron star is no ordinary celestial body. It's a cosmic paradox, a place where the laws of physics seem to break down and the fabric of space-time is twisted beyond recognition. These stellar remnants are not just objects in space, but profound mysteries that hold the potential to unlock some of the deepest secrets of our universe. So, what exactly is a neutron star? To understand it, we first need to witness the spectacular end of a massive star's life. When a star, much larger than our sun, exhausts its nuclear fuel, it can no longer fight the overwhelming force of gravity. This causes the star to collapse inward, triggering a supernova explosion, an event so powerful it outshines entire galaxies. What remains after the explosion is the neutron star, a compact, superdense object that is, quite literally, one of the densest things in the universe. When the star's core collapses, the atoms in the core are crushed, causing protons and electrons to merge into neutrons, particles that have no charge and are incredibly stable under extreme conditions. These neutrons form a tightly packed, ultra-dense core, and the result is a neutron star, an object so small, yet so massive, that its gravity is intense enough to warp space around it. At this point, the neutron star is almost unimaginably dense. If you could take a single teaspoon of its material, it would weigh over 6 billion tons, far heavier than anything we can comprehend on Earth. But it doesn't end there. Neutron stars are not just incredibly dense. They are also remarkable for their extraordinary behavior and the extreme environments they create. Let's pause for a moment and consider the sheer force of gravity on a neutron star. The gravitational pull on its surface is so immense that it would crush anything that ventured too close, literally bending and warping the very fabric of space-time. To stand on the surface of a neutron star, if it were somehow possible, would mean feeling a gravitational force 2 billion times stronger than what we experience here on Earth. The pressure would be so intense that atoms themselves would be forced to collapse into a uniform mass of neutrons. But gravity isn't the only thing that makes neutron stars so fascinating. Many neutron stars possess incredibly strong magnetic fields, some of the strongest in the entire universe. These magnetic fields are so intense that they can influence everything around them, warping the paths of charged particles and creating dramatic bursts of radiation. These magnetic fields can be 1,000 trillion times stronger than Earth's, creating environments of unimaginable power. It's the strength of these magnetic fields that gives rise to one of the most extraordinary classes of neutron stars, magnetars. Magnetars are neutron stars with magnetic fields so strong that they can distort the fabric of space and time itself, emitting bursts of high-energy radiation that can affect instruments on spacecraft thousands of kilometers away. These bursts of radiation are so powerful they can even cause disturbances in Earth's own magnetic field, acting as a reminder of just how extreme the universe can be in places we can barely comprehend. Neutron stars are not only known for their size and magnetic power, they also have one of the most intriguing and captivating characteristics of all: their ability to spin incredibly fast. Some neutron stars spin at speeds of several hundred rotations per second, which is mind-boggling when you think about the extreme conditions required to sustain such a spin. This fast rotation gives rise to a phenomenon known as a pulsar. Imagine standing on a spinning top, except this top is the size of a city, weighs more than the sun, and spins at mind-blowing speeds. Pulsars emit beams of electromagnetic radiation, much like the light from a lighthouse sweeping across the sky. But these beams are not just any light. They are highly concentrated and travel at almost the speed of light. As the neutron star spins, these beams sweep across space, and we see them as regular pulses of energy. Depending on the pulsar, these pulses can be remarkably regular, almost as precise as atomic clocks. This rhythmic pulse is what gives pulsars their name and makes them incredibly useful for scientists. By studying these pulses, astronomers can measure the spin rates of neutron stars, test theories of gravity, and even detect ripples in the fabric of space-time itself, known as gravitational waves. While we can observe the behavior of neutron stars from a distance, what happens deep inside these stellar remnants remains one of the greatest mysteries in physics. What does the core of a neutron star actually look like? What happens to matter under such extreme conditions? For years, scientists have speculated that inside some neutron stars, the core may consist of quark matter, a form of matter so dense that it is made up of the fundamental building blocks of protons and neutrons, quarks. In such extreme conditions, quarks may no longer be bound into neutrons, but instead, they may exist in a free-floating state. This strange form of matter could hold the key to understanding the behavior of matter at its most fundamental level. But these theories are difficult to test, as we can't yet reproduce the extreme densities and temperatures of neutron stars in a laboratory. What's more, the exact nature of the interior remains elusive, leaving us with an entire realm of unknowns that continue to baffle even the most advanced astrophysicists. Could the interiors of neutron stars hold the key to understanding how the universe was formed, or even how matter behaves at the most extreme levels? For now, these questions remain tantalizing mysteries, awaiting the next breakthrough in observational astronomy to reveal their secrets. But we don't have to look inside the star itself to discover the true power of neutron stars. We can study the gravitational waves they produce when they collide and merge. These ripples in space-time were predicted by Einstein's theory of general relativity more than a century ago, but it wasn't until recently that we were able to detect them directly. In 2017, astronomers made an unprecedented discovery. They detected gravitational waves from the collision of two neutron stars, an event known as GW 170817. The resulting explosion sent shock waves across space, producing not only gravitational waves but also bursts of light, X-rays, and gamma rays. These signals reached Earth, giving scientists a first-ever glimpse into the dynamics of neutron star mergers. Such mergers are not just spectacular cosmic events. They are also responsible for the creation of heavy elements like gold and platinum, which are scattered across space and contribute to the matter we see in our own solar system. The study of these collisions is helping us understand how the universe produces the elements that make up our very existence. Neutron stars are more than just celestial objects. They are a lens through which we can peer deeper into the mysteries of the universe. From their extraordinary density to their pulsating light, from their magnetic fields to the powerful gravitational waves they generate, Neutron stars challenge our understanding of the very nature of matter, space, and time. They are also cosmic markers, telling the story of the universe from its earliest moments. The study of neutron stars gives us a window into the past, shedding light on the forces that shaped the galaxies and the fundamental elements that make up the universe. These tiny, dense remnants are more than just the remains of dead stars. They are the building blocks of the cosmos, the key to understanding the fundamental nature of space-time itself.